Now everybody makes some comments about our non-anniversary conference, and I don't want to be like everybody, so I don't want to say much in this direction. Still, I need to mention that when I just finished work in France and was going to Moscow, Anton told me that I should learn some geometry in moduli spaces, and I should work with Sergei and with Igor. So it took me many years. I was not a very good student in this sense, and it took me many years to indeed write the first paper with these two brilliant collaborators. But still, I think we succeeded. So today I'm going to tell you something about what we did and what should be done in this direction. And my talk will refer a lot to what happened at the John Chaika's talk, but in reality I will be working with quite a different object. So let me start. And where is the chalk? Yeah, here. So it's a joint work with Sergei Landau and Igor Krichever. So the main protagonist of today's day is called the real-normalized differential. So I'm going to start with the definition, which is pretty simple. I take a meromorphic differential on a Riemann surface and I say that it's real normalized if simply its periods are real. All its periods are real. So this notion, in reality, has a lot in common with the concept of harmonic function on a punctured Riemann surface. Because once you are given a real normalized differential, you can consider an abelian integer, take an imaginary part of it, and what you will get this way, it will be a single-valued harmonic function if your differential was real normalized. And of course, if you were given a real-valued harmonic function on a Riemann surface with punctures, then you can find locally a conjugation to this function, and then you can consider differentials that will be constructed as your dx plus I dy, where x and y are these two harmonic functions. So basically what we are talking about is morally very close to the notion of harmonic function on punctured Riemann surface. So they were defined some time ago. I think that the main creator of this notion was Igor Krichever and Sam Gruszewski, who collaborated a lot, and they proved many things that I don't understand, so I will not pretend, especially in front of Sam, that I do. I will just mention some keywords to let people follow if you are interested in the motivation. So it comes from a rhythm perturbation theory for algebraic geometric solutions of the integrable systems. This was the first motivation. And it was done by Igor and Sam. So, and the rhythm theory can be very useful when you try to understand what's going on in the geometry of moduli spaces when you deal with a punctured Riemann surface. A few famous results were obtained by this technique where real normalized differentials played their role. In particular, there was a new proof of the Diaz bound on dimension of complex subvarieties for the moduli spaces, and the proof of conjecture formulated by Enrico Arbarello that deals with cycles in Mg of dimension G minus n, and so on. So I will just mention maybe that there was a Diaz theorem and Arbarello conjecture. But in my talk, we are not going to speak a lot about the algebraic geometry and associated constructions, even if it's cool to understand that what you do can be useful for other mathematicians as well. We will concentrate more on the pure dynamical aspects. Namely, my main object will be the so-called absolute foliations, or absolute period foliation, or real foliation, or that I will define for this object. And its close relative was exactly the person that John treated in his talk with respect to holomorphic differentials. So let me give you some definition and explain what is the main object. Oops. So we are going to define the absolute period foliation. So the idea is that we consider the differentials, we fix their periods or group of periods, and we want to consider all the pairs with surface plus a differential such that the differential would have the same periods as we fixed. And if we are in this situation, then it means that we live on the same leaf of our absolute period foliation. So our goal is to study the stratification and the corresponding foliation of the space of real normalized differentials. And I will restrict myself now to a particular class of them. Namely, I will want that my differential has a single order two-pole. So what is the foliation? As I told you, that we fix one group of periods, and we will consider the leaf. Maybe I should write it. Leaf of my foliation, of this foliation, passing through my real normalized differential phi. And so this is the connected component that contains phi in the locus of all differentials whose subgroup of periods coincides with the subgroup associated with phi. Sure.
I don't know how to paint a picture of this. So is it okay if I think, for instance, of it as just like taking a vertical strip and gluing another copy on top? Would that be an example of what you're talking about?
It's okay, but I will proceed with a model which will be very explicit, and it will simplify, I think, the picture. So now I just want to put you kind of in a context, and then exactly the goal of my talk is to introduce combinatorial model that allows us to do some dynamical things we like, basically. So actually, going back, this looks pretty much like what people do with holomorphic differentials. And in this case, they are very used to the notion of absolute period foliations. So you fix this pair of phi, but typically it's not a part of R, but a part of the set of complex numbers. And then you consider the stratification and do exactly the same thing as I wrote here. So it's known under many different names. People used to call it absolute period foliation, real foliation, kernel foliation, isoperiodic foliation, and it's always the same person. And this person is very nice, invariant under the action of the Teichmüller law and the holonomy map. And people know a lot already about both the geometry of leaves and its ergodic properties. In particular, it's not hard to see that if you fix the genus of your surface, so the dimension in holomorphic case, dimension of the leaf is 2g minus 3 if g is not too small, and it's transverse to the orbits of SL2R actions. And so typical questions that dynamists like to ask is the question of transitivity, ergodicity, and geometry of leaves. Yes, yes, you are right. Thank you, Pascal. It means that we are in a principal stratum. Yes. So in holomorphic case, the answer is now almost known for basically everything we touched. So I will partly repeat what John already said. So if we fix we live in the principal stratum, then our life is really pretty much determined. Because in this case, it was proved several times that our absolute period foliation is ergodic. And the first proof is, okay, the first result is this direction is obtained by Kurt McMullen, who treated the low-dimensional case. Actually, he treated the case of arbitrary genus. He was able to understand how the fiber of period mapping looks like, to make some geometrical statement about it, that it's a slice of the Schottky locus in the Siegel space. And then using the understanding of how this Schottky locus can look like when G is small, when G is less than or equal than 3, he got the ergodicity of the corresponding foliation. And then in the principal stratum, it was proved in the full genericity twice, at least. The first result is by Bertrand Duroan and Stefano Francaviglia and Gabriele Casamiglia. They obtained so-called the transfer principle. Namely, they were able to present these things in a way that they could apply Ratner's theorem to get the statement of ergodicity. Because in reality, they prove much more than just an ergodicity. They have a kind of classification of possible shape of the leaves that they can get. And because they could describe it in terms of the action of several groups. And once they did this, Ratner's instruments started to serve them, and they were able to extract ergodicity from this context. And another proof is by Ursula Hammenstadt, who had completely different approach because she used what was done by Kurt and then introduced some smart induction on the genus that allowed her to prove the ergodicity, but in some sense by more topological instruments. Then for non-principal stratums, the situation remained more complicated. And for a long time, the only known result was the one by non-principal stratum. Was an observation made by Barak Weiss and Pat Hooper, who treated the case of a very specific surface. And it's in some sense my favorite surface because it's Arnoux-Razi. Oh, sorry, Arnoux-Yukoz surface and foliation on it. So it's a very particular situation, since on the one hand, it's minimal, but once you touch the parameters a little bit, it stops to be minimal, so it's very unstable. But at the same time, it's self-similar, because the Arnoux-Yekos interval exchange transformation is known to be self-similar. So their case, when they proved not the ergodicity, but transitivity in this situation. They found a dense leaf. And then later it was slightly generalized by Tom Schmidt and Do, who also treated some very particular pseudo-Anosov's examples. Once again, they used self-similarity and instability. So then it remained open for a long time, the question about ergodicity and possible information on geometry of leaves in non-principal strata. So there are very recent results by Karl Windsor. And these things that John explained us here, so the theorem by John Chaika and Barak Weiss, which is conditional on strong results of other people. So they arrived to the ergodicity for non-principal strata. And that's more or less what do we know in the case of holomorphic foliations. So my goal is more or less to repeat the same plan. However, our situation will be very specific, because I will not be allowed to use any of the instruments that people use here. And so I will stop on a kind of a smaller result with the hope that we can arrive to something stronger. So in order to explain you how we do that, I need to introduce our combinatorial model. And we will do the following thing. So this is our differential. I will call my surface C, and C will be a Riemann surface of genus G. So I can take two important points. First, we agreed that we have only one pole, and this pole is of order 2. So this will be my pole, P, pole. And then I want to take a point which is not a pole and not a 0. So this will be Q. Then I can consider the tangent plane to my surface at the point Q. And I can choose a line there, which is a tangent to the germ of the curve given by the equation like that. And I will choose a, so this is a germ. And I want to be tangent to this germ. And I choose the orientation in a way that the orientation choice, I have a line, so I'm allowed to orient it. Orientation will be given like that. And I want it to increase. So this allows me to define a smooth-oriented line field on my surface. So on the complement to the set of poles and zeros, to be more precise, because I chose Q to be some nice point, not a singularity. But then if I have a smooth-oriented line field on the surface, I can extend it to my singularities, since I have only a finite number of them, right? So I can extend it to the pole and to the zeros. And at the current moment, let me be like my colleagues in the holomorphic case and stick to the situation when we have principal stratum. So all my zeros are supposed to be simple. It will be somehow important for me. So let's see what's going on when we look at the pole and what's going on when we look at the zeros. So it will work like that. Just a second. If we have a 0 If it would be of order k, then locally I can think that my differential would look around there as z dz. Because around this 0 locally, I can introduce such a coordinate. And in this way, if we look at this equation that is supposed to define my vector field, I will get 4 directions. They simply correspond to the roots of I and minus I of order 2 in our case. So if 0 would not be simple, it would be the same, but it would appear order of the 0, and here we would have not 4, but 2k plus 2, where k is the order of the 0 directions. And so since they are all roots for I and minus I, what will happen is that there will be lines, so there will be this 0, and there will be lines that go in and out. So I will make a picture of 4 because I told you that they are supposed to be simple. And those who correspond to I, they will go outside. And those who correspond to minus I, they will go inside. So they will alternate their direction, something like that. And then what's going on inside, around the pole, we also can introduce some coordinates that would look nice near this point. And of course, since it's a pole of order 2, we agreed, then it should be z minus 2 dz. And so the integral lines of our vector field in this case, they will be simply the infinite number of tangent circles. So we have here like integral lines of the vector field. There, infinite number of tangent circles. And the orientation is chosen in a way that this part, the real part of it, increases. So the integral lines, those that are passed through zeros, we will call them the separatrices. So the separatrices, obviously, they're supposed to connect some singular points, as usual. But then it's quite easy to understand that one separatrix cannot connect to different zeros. It's simply forbidden because of the conditions that we made about the fact that this should increase. And at the same time, it cannot go back from the pole from 0 to itself, and it cannot go from the pole to itself. So it has only one destiny. It should connect zeros with pole. There is only one thing that they can do. So their job is to connect zeros with the pole. But once we understand it, what do we have here, apparently, is that we have some kind of a graph with 2g plus 1 vertices. 2g correspond to zeros, and 1 correspond to this particular pole. And the edges will be simply the separatrices that go in from 0 to this particular pole. And since zeros are simple, then each 0 has 2 departing separatrices, as we agreed. So what do we have? We have a graph. It has 4g edges. They all go to the pole. And no 2 separatrices are homologous to each other due to all these restrictions that we put. So we have 2g plus 1 vertices. And if we apply a Riemann-Hurwitz formula, we will see that we have one face for this graph that we define. And once we know that we have one face, then we can cut through these separatrices, and we will have something like 8g gon, some polygon to treat. And at this moment, we are ready, more or less, to see what will be the picture that we are interested in. So it will look as follows. We will have pairs. Maybe I will make a picture here, just not to spend your time on erasing. So for each 0, we will have 2 cuts that are going to infinity, and they are going to meet somewhere in our favorite pole. And then they live at the same horizontal level because we have a real period. And then we do the same for each 0. They can be located differently with respect to each other, but we will have a picture like that. I hope, Jadev, that it's more explicit now once we see the situation. And so also it's true that if we are given such a picture, when we have all these vertices that each couple lives on the same horizontal level, but different couples live on a different levels, and we have all these cuts, there is a way to construct the surface with a real normalized foliation, real normalized differential on it. And in order to do that, you simply need to glue it, respecting the following natural rule. You want to glue your left border to the right border of the corresponding cut. So you glue people like this, and the right person should be glued again to the to the left one. So, and the same we do for every cut that we have, and this is our combinatorial model. Basically, you see, there is still no dynamics, but it's already something extremely explicit and something that lives basically on the plane, and you just cut the plane and we can glue it back and get the structure that we are interested in. So you take, if you want to formalize it, you say that you take pi qi, and you want that the real parts are different, but the imaginary parts coincide. And different imaginary parts you define for different pairs. That's what corresponds to the fact that they live on a different altitude here. And so then you reglue in accordance with the rules that I told you, and you simply take dz, and once you reglue it all, it becomes a meromorphic one form, because this point at the infinity is a singularity, so it becomes a meromorphic one form, and we call it phi pq. And this phi pq is real normalized because the group of its periods is simply generated by the differences between corresponding pi and qi. So that's our model. Then there is a natural question: what corresponds to the shift of all pi and qi at the same time? The answer is very natural. It just corresponds to the change of the initial points that we used to make all this construction with the vector field and so on. You remember I took a arbitrary point q. I could take a different point, and it would correspond to such a shift. But then the group that you have will not change much because only the difference matter. And that's exactly what one could expect in this situation.
Can I ask a question?
Sure.
So you have a unique pole.
Yes, yes.
The residue is 0. How does it reflect here? You have to sum up something equal to 0.
Yes, that we will do. You are right. So we will expect that the sum of this pi, qi minus pi should be 0. We need a normalization condition. Thank you. You are completely right. That's true. Okay. So once we arrived to such a model, we can proceed with some results finally, because I'm speaking for already half of the time, and I did not explain any theorem, so we need a theorem probably. Let's put some theorems. Just 1 second. I want to understand in which order. Okay. So indeed we have a renormalization condition. So we can say that the sum of them should be 0. And before I proceed with some dynamics that I announced, I probably need to say a few words about some non-degeneracity. So first, let me introduce a kind of a new language for this model that we discussed. Namely, in order to treat it somehow, to study its combinatorics, I need to present it in a way that is very standard for people who are doing knot theory and some arc diagrams and so on. Mainly, I can think that I added some kind of a horizontal line here. And instead of looking at these half rectangles or horseshoes, as we called it at the beginning, but then we gave up because many people use horseshoes in dynamics. So instead, it's better to see that there is an arc, and you just need to remember how exactly these arcs are linked with each other. So you can code your combinatorial part of this picture by arc diagram. Of course, in such a way, you are going to lose your metric information about the periods, but as in case of interval exchange transformations, we can have a rosy diagram, and it will contain some information on what we are studying, even if we don't remember the length at the moment. So this is a key notion for us. It's an arc diagram. And now we ask ourselves, either it's true that any picture like that gives us something non-trivial in the sense of meromorphic differentials with a single pole or not. Or in a similar way, is it true that any arc diagram would serve our purpose to construct a surface with a meromorphic differential on it? And the expectable answer is it's not true, of course. Not everybody fit our purposes. So there is a theorem. The theorem is formally by us, but in arc diagrams business, it was known much before we got interested in these things. So the result of cutting and gluing the horizontal line, I will write it and then explain, okay? The horizontal line the connected line if the intersection graph of the arc diagram is non-degenerate over F2. So first, let me explain you why do we care. Actually, the conditions that we have a unique pole using this type of model is equivalent to the fact that if we take some transversal, some horizontal transversal, and we follow what happens to it when we start to reglue it. So we wanted to, after all these cuts and gluing, we want to obtain the connected line again. Otherwise, it would be, yeah.
Sorry, could you say what you mean by cutting and gluing the horizontal line?
I mean that here we have this model when we say that this border, the left border should be glued to the right border, and the right border should be glued to the left border, and these kind of things. So now what I want is that if I start with some horizontal person, I want this person to visit all these places and to be a connected line again after I follow my procedure, because otherwise it will be a contradiction with the fact that we're supposed to have just one pole. So, for instance, what's going on? This guy starts here, then it should continue here. Maybe I should color more people. So if it goes here, then it was supposed to exit from here, and it's not good. So the picture I made, it's bad in this sense. But if it would be more intelligent and it would visit all these pieces and cover all the spaces here, then we would be more lucky, and it means that the picture that we have is good for our purposes, and indeed it codes some pair surface plus meromorphic differential. So our goal is to understand how to express this condition on some kind of understandable combinatorial language. And once we switched to the language of the arc diagrams, we found out that it was already done before us by all these people who were studying arc diagrams. And they proved that the necessary condition for such a purpose is that the intersection matrix of the arc diagram is non-degenerate over F2. So there is a way to, using simple combinatorial language, to distinguish the pictures that are good from those that are bad and meaningless for us. This was the first observation. Now we need to do the next one. So let me say the following thing. Can we? Namely, I want to understand something about my foliation. I want to say how many, to see how many connected components I may have for the leaf, and how can they look like, and so on. So we take we prove the proposition, maybe it will be simpler. So I want to estimate the number of connected components in the space of generic meromorphic differentials, generic real-normalized. Meromorphic differential with single pole of order 2. And no other poles. So this number of connected components, exactly because we are able to present it as arc diagrams, was already computed by people in arc diagrams business. Double factorial means that we take only odd numbers. So what does it mean, what is written here? Simply that actually the set of non-degenerate arc diagrams with 2G arc is exactly one-to-one correspondence with the given one that can be connected by a smooth path in the set of our diagrams having the same arc diagram, while cut diagrams with different arc diagrams belong to different connected components. So if we want to compute the number of possible connected components here, at the moment we don't think about absolute period foliation. We just count the connected components of this of the stratum modular spaces. So if we need to compute this, we just need to compute the corresponding arc diagrams. And this can be done by some standard combinatorial technique. And so we computed these things as well. It was more or less automatic. Now, yeah?
Sorry, what does generic mean here?
Generic means that all zeros are simple. There is nothing degenerate in this sense. You want them to be incommensurable, but for this it's not important. But in general, for what I will say in the future, we assume that these qi minus pi, they are incommensurable rationally, because I want to exploit some procedure that looks a little bit like Euclid algorithm. But here the word generic just means that we want all the zeros to be simple. For arc diagram does not know anything about the length, so it doesn't care. So now let's switch to this absolute period foliation and try to understand what's going on there. So as I told you, we have a pair. This is a surface, this is a differential. And we consider the additive subgroup of R that consisting of periods of our differential. And if it's generic, our guy, then it means that L phi coincides with one of Z linear combinations combinations of pi minus qi. So homology classes of the closed curves that are represented by arcs in the complement to the cuts connecting pi to qi form a basis in homologies, and then the integral that we take of dz over such an arc is independent of the choice of the arc. So this subgroup is generated by not more than 2G generators. And each subgroup can be realized like that. So these subgroups, they can be divided into two types. Either they are discrete, either they are not. So they are dense. If they are discrete, they are those who are generated by just one element. It's pretty degenerate situation. And if we have at least two people who are non-degenerate, then it means that we have a dense situation. So we will be interested in the case when we don't have just two incommensurable people, but we have total incommensurable case. So we have exactly 2G generators. And we can consider the space of all the real normalized meromorphic differentials with a single pole of order 2 on a genus G surface. And we can consider a subspace there, which is a locus of our period foliation. And so we take L phi equal to L. So we prove the proposition, very simple one, that tells that if we take dense L, dense L as a dense subgroup of R, AL is dense in RG. So our locus is dense then in the set of all pairs, set of real normalized meromorphic differentials. I don't want to write it once again. So if L is dense, then AL is dense as well there. And L is very often dense, as we discussed, if we put this in commensurable condition. And now the longest theorem that we proved is the following statement. So theorem. That we take a totally incommensurable one form. The corresponding locus L phi in Rg contains at least as many connected components as the set of conjugacy classes GL to GZ factor SP 2gz. So in case of g equal to 1, we have just 2 connected components. And if g is greater than 1, we have infinitely many connected components. So this theorem was quite surprising, because it's very different from what people are used to have in the case of holomorphic differentials. You do not expect to have so many of them. Normally, you have just one there. And I'm supposed to comment a little bit, probably on the proof. And then I will tell you what we want to have using the same machinery. So the idea of a proof is based on the two following observations. First is a lemma that tells us the following thing. Before I state the lemma, I introduce a notion. I will call an arc diagram a G caravan if this arc diagram, which is formed by two G arcs, looks like that. That we have these arcs, they break into couples, and each couple is linked, but there is no other link between the members of different couples. So we somehow unknot the arc diagram, and the unknotted version of it will be called the G caravan. G because G is the number of couples. So it's caravan because they look like camels. And so what we proved is that for a totally incommensurable period subgroup, L phi, each generic cut surface means that we use this model that I told you where we cut through these vertical lines. So each generic cut surface can be connected by a continuous path in AL phi. It belongs to, so in its locus, to a G caravan cut surface. And this lemma would never be proved if Sergei Landau would not study knot theory. Because, I mean, it's all based on the application of so-called second Vassiliev move. To the arc diagrams. So what is the second Vassiliev move? I will explain you, but I prefer to do it on a more kind of language that requires me a little bit Rose induction. So let me recall how the cut surface look like. We agreed that it's something like that. So let me fix that it's just a couple. In reality, of course, the theorem deals with the situation when we have much more of these horseshoes, but at the moment. So what I claim is that, look, what changes if I will take one of my horseshoes and move it a little bit horizontally? Nothing. The picture remains the same. So if it had a period A and period B, I move, for instance, I fix A and move the big I a little bit, and nothing changes. But then imagine that I started to be kind of a little bit aggressive and move it stronger and stronger, at which moment we have some kind of reconstruction of our picture, when it changes. It changes at the moment when the big I arrives to the border of the A person, for instance, right? And what happens at this moment? Once we touch this border, we will be obliged to jump to the position that lives on another part of our cut surface, right? So maybe I should draw it in a more accurate way. So I move a little bit this person, and the person arrives to the border here and then jumps directly here, right? So it's the moment when we have some crucial change, the phase transition. so once we would do this phase transition, what do we have as a picture? We would have still A on its place, but the P person would change its position. So if I move it again, then from this critical point, the B would lose a little bit of its width, because instead of being B is before, it will become B minus A, right? And you can do a similar way, moving A with respect to B. And so what you have, and at the same time, you do not leave your leaf of your foliation, you do not leave your locus, at least. So what I want to say is that you have some kind of application that changes the combinatorics, and this change exactly corresponds to the second Vassiliev move applied to my arc diagram, what's going on with them in a combinatorial sense. And at the same time, something is going on with their length, and this procedure recalls pretty much a simple Euclid algorithm, or I don't know, Farey map, depends if you want to renormalize or not. So it gives you a description of some combinatorial process that is already described by knot theorists when you do things like that. And this is exactly what is called, so this remains stable, and this guy moves. And it moves to the way that this was still stable, and him becomes very big, and like here. And these kind of things, similar movements, they are all called the second Vassiliev move. And from metrical point of view, we do something that recalls us Euclid type algorithm. And so, we do not leave our favorite locus doing this procedure. So what does it give us? It means that if we have this lemma, then we can say the following thing, that any G caravan in this locus defines a basis of the Z module L phi. And this basis is defined by the length of corresponding arcs. So any two such bases are related by some GL to GZ transformation. On the other hand, any G caravan determines the basis in the first homologies. From one basis to another one, we switch using the symplectic group. Why it's true? Because there is a symplectic form in the first homologies that corresponds to the intersection form, simply. So once we know that we have this, it means that we have the statement that I announced somewhere here. So this GL corresponds to the change of the basis due to the change of the length. And this SP corresponds to the change, symplectic group corresponds to the change of the basis that arrives from the consideration of L as a polarized symplectic module. So, because there is a natural symplectic form in homologies. And due to this fact, we have such a statement. So before I finish, I want to say a few words what else was done very recently and what we plan to do. So what else was done? There is a very fresh, not written yet result by Marina Nenasheva. She is a PhD student of Sergei Landau and Armand Lano, partly working with me as well, and she proved the following statement. So once again, you take a subgroup of R plus, which is R plus means that not that they're positive, but that it's a group with additional structure. And then you have this isomorphism, and you consider this isomorphism the isomorphism of the polarized subgroups. And polarization comes from the existence of symplectic form in homologies. So you have AL of I don't know, of phi, which is a polarized group of period. Maybe I should not call it phi, let me call it kappa, because it will not be one polarized group of period, and kappa corresponds to stratification. So it's a description of zeros and poles. What I mean is that here I told you what's going on in the principal stratum, and now we allow ourselves to consider different options. So this gives a stratification to us. So she claims that AL of kappa is connected, theorem by Marina Nenasheva. AL of kappa is connected in the following cases. She does not claim that she knows what's going on in other cases. So be aware, it's not like we know that in other things it's not true. It's just we only can prove it in this situation. So that it's connected in the following cases. So first is when this kappa is 1 to g minus 2. It is exactly what we did now. So be aware again, in this theorem we fixed this phi and then proved what's going on with how many connected components do we have for the corresponding locus. And in this situation we do slightly different thing because we do not fix any phi. We just consider it as a polarized group of periods. So the second case is when we still have all the zeros simple, but we have two different poles. And the third case is when we have 1, 0, which is not simple, and the pole is still the only one of order 2. Her technique is very similar to what we did now, so she also uses the arc diagrams and so on. The key difference is that, for instance, when you have not one pole but two, you don't deal with the arc diagram, but you switch to the Horde diagram. You get a circle instead of a line, and so you have to make a slightly different analysis of combinatorics, but it's still a familiar object. And the last thing that I want to say is what should be done in some sense. And in this direction, there are two directions. One is what Marina is trying to do, so to treat the non-principal strata and to understand there as well as we can what's going on. And the second direction is to go deeper to ergodic properties. Principal stratum and ergodic properties. It can be kind of the first step in our understanding how the absolute period foliation may work for meromorphic differentials in general, even if this class is a very, very particular one. But Bertrand Duroan and Stefano Francavilla and Gabriele Casamiglia are working on a different approach to the meromorphic differentials. They try to generalize their transfer principle, but our case is not covered by their activity as well. So I think I said everything I wanted to say. Thank you very much.